Hi, this is Mr. Merrill, and this video is about the difference between conservative and non-conservative forces. So, we have to start with this definition of working. And I want to remind you that even though I have a W here, it's kind of misleading that I use the symbol W. Because working itself isn't numerically anything. It's just a process that we call either adding or removing energy from a system. So really what this number that you're computing, what this W actually stands for, is that amount, that numerical amount of energy that has either been added or removed. Working itself is not a number. It's just a process. So let me remind you of what this equation means. So this little f with the two vertical bars, that means the component of the force that is parallel to the direction of motion. D is the distance that force is applied over. And the plus or minus sign, well, that's just saying, is that component of the force in the direction of motion, meaning positive, it's adding energy to the system, or opposite of the direction of motion, negative, so it's removing energy from the system. So you'll see that both non-conservative and conservative forces follow this numerical relation, but it's good to distinguish between the two, and you'll see why. So we'll start out with the simplest example of just saying a gravitational force acting on a box. And the whole difference between non-conservative and conservative forces can be seen through the idea of going away from a point and then coming back to it. So starting at, say, A, going somewhere else, and then returning to A and see what happens. So a conservative force will say, if you go on that journey away and then back, the total amount of energy you've added and removed will be zero. That's what conservative means. It hasn't added or removed any energy if you go back to the beginning point. If you reverse the process. A non-conservative force it says you go on a trip and you go back. Well, you forever have changed the amount of energy in that system. That you have not conserved the energy in that system. So we'll start with this example and we'll see some examples of other ones. So this example is going to show how gravity is a conservative force, that a net journey does not change the total energy in the system. So we'll start by moving a block up. So it starts at A and we move it up 10 meters. The whole time, a 5 Newton force, the weight of the box, the magnitude of the force of gravity, was acting for a distance of 10 meters, and it was acting in the opposite direction of motion. So we were moving up, and the force was directed downwards. So that means we got to place a negative sign here. It doesn't matter what was actually moving the box up, because we're only considering what the force of gravity is doing. So numerically, this says that negative 50 joules of energy was removed by the process of the working done by the gravitational force in this first leg of the journey. But then we're going to imagine a second leg of the journey where the box returns to its starting point. Okay? So there in that second leg of the journey, it was a 5 Newton force acting over a distance of 10 meters. But on the second leg of the journey, the force was in the same direction of motion. So instead of a negative, it's a positive sign out in front. And this tells us that in that second leg of the journey, the force of gravity added 50 joules of energy to the system. So the total journey, going away from A and then returning to A, we have not changed the amount of energy in the system. So I did a very simple case of a box just moving up and down, but this is true no matter the path we took. We could have taken a much more complex path. At every point in the path, we could have calculated the component of gravity that was in the direction of motion, and this is actually a calculus problem if you do that, but the result is still the same. at the end part of the video, if you want to stick around, I'll kind of show this with a slightly more difficult path, just to, for those of you who are interested, to give you some confidence that this holds true for paths that are more complicated than just straight up and straight down. So that was a conservative force of gravity. Another common example of a conservative force that we'll see is the spring force. So an elastic force in a spring, and specifically in an ideal spring. So in an ideal spring, you can have the spring work against you. So you can push a spring in that will remove energy from a system. But then releasing the spring will allow that same amount of energy back. And if it's an ideal spring, meaning that there's no losses due to a transformation of thermal energy, you get the exact same energy back that you put in. So it's the same thing here, adding everything up to equal 0. So let's look at a non-conservative force. We'll look at a non-conservative force, and specifically the one that you'll most commonly see in the problems that you'll be asked to solve, and that is the force of friction. So it's a non-conservative force, and you'll see why. So this is obviously not the complete force diagram, and that's okay because I really only care about what the force of friction is doing. So we have to imagine a box moving, starting at A and moving to the left here. So the entire time we'll say the force of friction is exerting a 5 Newton force to the right. So we move the box to the left. So the entire time that 5 Newton force of friction was being applied. So let's think about what was happening in this first leg of the journey. So in this first leg of the journey, we had a force of 5 newtons over a distance of 10 meters. And we want to recognize that the force here was in the opposite direction of motion. We were moving to the left, the force was pointed to the right. So this must have been removing energy from the system. So the total amount of energy removed from the system by the force of kinetic friction here is 50 joules. Now what's different is that unlike the force of gravity, which was down the entire time, is that when we move back, this changes direction because it's always going to oppose the direction of motion. So when I do my second leg of the journey and I move back from here back to A, in that second leg of the journey, it was still a magnitude of 5 newtons over a distance of 10 meters. But because that force flipped, it remained in the opposite direction of motion. So it continued to point in the opposite direction of the velocity of the motion. So this is still a negative, and our return journey to A took away another 50 joules of energy from the system. So instead of being back to where we started as a change of no energy, like we saw with the force of gravity, here we have not conserved the energy of a system with a trip from somewhere and back. In fact, we have removed negative 100 joules of energy. And there's no way around this. Any path you imagine going there and back will always end up removing energy from the system. And I think this is most clearly seen with kinetic friction. So we're going to look at another non-conservative force. Okay, so we talked about how the gravitational and spring forces are conservative, and you saw how the kinetic force is non-conservative. Finally, let's talk about some of the other kind of everyday forces that you're used to. So for instance, normal forces, static friction, tension. So we're going to show through one example, and you can kind of imagine other examples for yourself, is where tension acts as a non-conservative force. So to show something that's to show that a force is non-conservative, all we have to do is imagine a loop, so going somewhere and going back, where the energy either added or removed from the system at the end of that loop is not 0. That's all we have to do to show that it's non-conservative. So just imagine we back to the box from before, and I tied a string to the box, and I'm saying I'm going to lift this box at a constant velocity, vertically upwards, and I just want to think about the work that the tension force is going to do here. Okay, so I'm going to lift it upwards, and so tension was exerting a force of 5 newtons for a distance of 10 meters. And it was in the direction of motion, so that's going to be a positive. So the force of tension added 50 joules of energy to the system on the way there. So if I lift to the top with a force of 5 newtons, I'm allowed to do something with the force of tension that I could not have done with the gravitational force or the spring force, is I can choose on the return trip how big to make that force. So for instance, I lifted it up with a force of 5 newtons. Well, let's say on the return trip, instead of exerting a force of 5 newtons on the box, I'm just going to exert a force of 4 newtons of tension. So what is this going to mean? Well, the forces here aren't going to balance, so the box will, instead of moving at a constant velocity down, it will accelerate down. But that doesn't matter. I just want you to consider this equation. And if we think about it, so this is 4 newtons of force, 10 meters. It was in the opposite direction of motion, but that's only 40 joules of energy removed. So adding everything up, we do not get 0. So the reason that, say, the normal force and the tension force are non-conservative is simply because we can choose how big to make them on any part of the journey. So you can create these kind of closed loops where things don't add up to equal 0. So that's kind of the simplest reason I can give you as to why we would call them non-conservative forces. So what's the point of distinguishing between conservative and non-conservative forces if the energy added removal equation, that W equation, is the same for both of them? The useful thing to recognize is that, think about our potential energies. So energy stored in the position of a system. So a gravitational potential energy is associated with a conservative force of gravity. A elastic potential energy is associated with a conservative spring force, right, or a conservative elastic force. And there's analogies for all of this. So for example, conservative magnetic force or magnetic potential energy is associated with a conservative magnetic force. So the idea that I'm trying to get across here is that for any conservative force you can assign a potential energy. And you'll see in these calculations it's much easier to deal with potential energies than it is to deal with work. So for instance, a potential energy of gravity, all you need to see is the height above the ground. That is much easier to think about than, what's the component of the force of gravity, what was my distance that I traveled. So in recognizing the difference between conservative and non-conservative forces, I open up this idea of potential energies. So if you want to stick around, I'm going to do a slightly more complicated example. It's not necessary, but what I'm going to do is show this is this force of gravity adding up to equal 0 works even if I don't choose a straight up and straight down path. So you can stick around for that if you want to. So let's choose a more complicated path than just straight up and straight down. So let's go on a diagonal here, but we'll raise ourselves to the same height. Okay, so that'll be our first part of a journey. We're going to go on this diagonal, but we'll raise ourselves to 10 meters high. So I'll also, for simplicity, make this 10 meters over. So hopefully you can recognize this is a 1 square root of 2 triangle, and that this angle here is going to be 45 degrees. So What does that mean? Well, that means this leg of the journey, instead of being 10 meters, is going to be the square root of 2 times 10 meters. And you can check that in your calculator. And again, this says, this equation here says only concern yourself with the component of gravity that is parallel to the direction of motion. So if we look closely here, the whole thing, the whole force vector is not going to be in the direction of motion. There's only going to be one component of it. And I should have picked a clearer color for that. Let me make this a little bit bigger, make this red. So only part of the force of gravity is going to be in the direction of motion along this diagonal. And you can figure out how much of that is, because if we know this angle here is 45 degrees, this angle here is 45 degrees. So how would you find this component? You would just multiply the cosine of 45 degrees times 5, and you'll get, if you do that in your calculator, you get a number. And what I want you to see is that number, you can also check this in your calculator, is the same as the square root of 2 over 2 times 5 newtons. So I'll let you check that. This will be obvious for people who have taken pre-calc, why that is. So let's just group that all together. So I'm going to move this box along the diagonal. So on that diagonal motion, my force, the component of the force that was parallel to the direction of motion, was the square root of 2 over 2 times 5 newtons, times the square root of 2 times 10 meters. And isn't this nice? The square root of 2 times the square root of 2 is 2, divided by 2, that's 1, 5 times 10, 50. Okay? Now, let's think about going across. So, let me ungroup that. Okay, so now I can think about moving the box across following this path here. So, moving this box horizontally across, was there any component of this force that was in the same direction of motion? No. So for that leg of the journey, 0 joules. Now we can go down. So that's downwards 5 newtons, 10 meters. Oh, I forgot to say here this is negative, because that component for the first part was in the opposite direction of motion. And so for here down, we move downwards. Here the force of gravity is in the same direction as motion, so this will be positive. So in the last leg of the journey, we added 50 joules of energy to the system, and add those up, you get 0. So I just wanted to show you that works for every path. In fact, we can imagine much, much more complicated ones where we gotta go all over the place. And if you had the calculus to deal with that, you could certainly check it. But the idea is, as long as you return to A, the total energy added and removed from the force of gravity is 0. So that's an interesting result. Okay, so good for you if you sat through that.